Calculus Lesson 8. We're going to spend a little bit more time going into a bit more depth about the first derivative. Lesson 9 will then be about the second derivative. We're going to touch on exactly what these derivatives mean, what they're used for, when they are used, how they are used. They are very, very important to the whole context of calculus. So, let's start off by defining the first derivative. You've seen it referred to as y dash, f dash x, dy dx. They are all absolutely 100% interchangeable. It doesn't matter which you use. They all mean the exact same thing. And ultimately what they all mean is they all are talking about the gradient, or more specifically the gradient of the tangent. Just to remind you of gradients from a couple of years ago, that they're positive gradient. Down is a negative gradient. The way I always used to remember it is I always think of the positive one as a tick, because you can turn it easily into a tick. Alright, let's try an example and start understanding exactly what they're talking about, and we can now see it visually as well. They ask us to find the gradient of the tangent to the curve y equals 9 minus x squared at these three different points. So, when we find the gradient of the tangent, we know from the last lesson we've just got to differentiate it and find the family gradient. So the derivative of that is negative 2x, which is our family gradient. That is the gradient all over the curve, not specific to any point. If we want to find the specific gradients, we sub in those specific points. So let's have a look. If we try sub in x equals negative 1, so we look at our graph, it's at that point. We want to find the gradient of the tangent at that point. So that there's the tangent at that point. If we want to find the gradient, well, we can see just looking at it that that's a positive gradient. In other words, what that means is that the derivative, the first derivative, is going to be greater than 0. So let's just prove that algebraically. We sub in our minus 1 into our family gradient. So wherever there was an x, we replace it with minus 1, and our derivative therefore is 2. So our m of t, our specific gradient, at that point is a gradient of 2. What about when x is 2? Let's try that. Well, if we draw the tangent there, we can see straight away that that tangent is going to be negative. In other words, we know that the first derivative is going to be negative. It's going to be less than 0. But let's just show that algebraically. We sub in 2 into our family gradient. We get negative 4, which, as we just showed, is less than 0. So it's all making sense. Next, we'll try x equals 0. So at that point there. Now, that line there, as you can see, is actually horizontal. It is parallel to the x-axis. And what that means is it's going to have a gradient of 0. But just to check that, let's just sub in 0, and our first derivative is 0. This is a really key feature that we're going to be using throughout the rest of calculus and the rest of the next year. It is a massive. Y dash equals 0 actually lands up giving you turning points or stationary points. As you can see, that is the turning point of that parabola, or as we'll call it, the stationary point of that parabola. We used to work out the turning points of the parabolas by finding the axis of symmetry and then subbing in to get the vertex. And here's a new way to do it, and a much quicker, better way to do it is by using the derivative. So the important thing to remember, the turning point or the stationary point happens when the derivative, or y dash, is equal to 0. So to summarize that, when the first derivative is greater than 0, we have a positive gradient. When the first derivative is less than 0, we have a negative gradient. And when the derivative is equal to 0, we have a horizontal or flat gradient. And at that point, when y dash equals 0, we get the stationary point. So the big thing to take out of it is to find a stationary point, you let y dash equal 0. Then that stationary point could be a minimum, such as that one. If it's a happy parabola, the stationary point will be a minimum. Or if it's a sad parabola, the stationary point will be a maximum. So we're also going to learn to test these stationary points, to test to see whether they are max or mins. We call this testing their nature. But for now, let's try this example. Does the curve y equals x squared minus 6x plus 3 have a stationary point? If yes, where? So, first things first, we differentiate it. So the derivative of that is 2x minus 6. Now, as I said, remember that key point. Stationary points occur when y dash equals 0. Write that out. And write that out in every question. I do. I write it every single time because I want to tell the story. I want to show them what I'm doing. Helps me to get into a good habit and a good pattern. So stationary points when y dash equals 0. So 0 equals 2x minus 6. We'll then solve for x. Put the 6 to the other side. 2x equals 6. X will therefore equal 3. So there's a stationary point where the x value is 3. Now we need to find, we don't want the stationary x coordinate, we want the stationary point. So we want the whole coordinate. So in order to find the y value, we take that x value and we sub it back into y. So wherever there was an x in the y, we replace it with a 3. Next step, we'll expand it. So it becomes 9 minus 18 plus 3, which then becomes minus 6. And so we have a stationary point at 3, negative 6. Perfect. However, as I mentioned, we want to find out, is that a max or a min? In other words, we want to determine its nature. That's what they refer to when they say its nature. Is it a max or a min? So we want to learn how to determine its nature so we can actually work out the coordinate of the stationary point and then say, okay, there's a max at that point, or there's a min at that point. So here's how you determine the nature. And we'll do it continuing on with the same example. So what we're going to test is we're going to test our x values and our y dash. In other words, the gradient. That's what our little test box is. And we want to test either side of our current stationary point that we found. So we know when x was 3, which is the stationary point's x value, that y dash was 0. And when we test like this, that point, that middle point there, the y dash will always be 0, since it's a stationary point here. We're using the x value of the stationary point, so the y dash will always be 0. And so, when we sketch it manually underneath, a 0 gradient is just going to be a horizontal line. And now we want to test just on either side of that stationary point. We want to see what is the gradient doing on just the either side of it. Is it going up and then down? Is it going down and then up? So we want to test points just on either side. First we're going to test 3 minus, so something just less than 3. Ultimately, the closer we can test to the stationary point, in this case to the 3, the better off we'll be, but often it's just a balance between accuracy and convenience. So in this case, to make it a bit easier for us, I'm going to sub in x equals 2. So when we sub that in to our y dash, as you can see the work in there, we get 2 into 2 minus 6, which is 4 minus 6, which is negative 2. So in other words, the derivative at that point will be negative. And we'll put that in there. It's not actually relevant how negative, so what that number is. All we want to know is that it's negative, because that means we'll have a negative gradient there. And you can see what's starting to happen down the bottom. It's starting to draw the stationary point for us. So it's like a manual testing of the stationary point to determine its nature. So let's now test a little more than 3, a 3 plus. Again, the closer the better, but for ease, we're going to just sub in 4. When we sub that into the first derivative, and then expand it through, we get 8 minus 6, which is 2, which is a positive gradient. So we put the positive in there, which is a positive line, and you can see we've now manually gone and drawn ourselves our stationary point, which you can clearly see is a minimum. And so we can say we've got a minimum at 3, negative 6. And so for now, that's the way we're going to test the nature of our stationary points. We do a little x, y dash table, and we just draw out our gradient as to what happens on either side of that stationary point. Does it decrease, flat, increase, which means it's a minimum? Or does it increase, flat, decrease, which means it's a maximum? So we just got to go through this process. It's a little bit arduous, but something better is on its way. So for now, we just got to be able to do this. Let's do another example and give this a go. Pause me here and try this out yourself. Find and determine the nature of any stationary points of the curve f of x equals 4 minus x squared. Give it a go yourself, find the stationary points, and determine the nature. Let's see how you did. There's our function. First things first, we know we've got to differentiate it. We get negative 1 minus 2x. Then, as I said, every time we write out stationary points when our derivative equals 0. And so 0 equals minus 1 minus 2x. We'll then solve for x. Put the 2x on the other side, so 2x equals negative 1, x equals negative half. So we know that there's a stationary point at negative half. Now what we do is we sub it back into our y to get the full coordinate, to get the y value. We sub in negative a half back into our f of x. So we get 4 minus half minus a half squared. Lots of minuses there, and that's why this in particular, you've got to be very careful subbing it in, and I don't try to do my expansion until the next step. And in the next step, you can see that first minus becomes a plus, and the other one stays as a minus because negative a half all squared becomes a quarter. So the bracket becomes a quarter, so it's minus a quarter. So you've got to do that step very carefully so you don't make a mistake with your minuses. Then to simplify that, probably best to just put it in your calculator, or you can calculate it in your head, or lowest common denominator, whatever's easiest for you, and you'll end up getting 4 1/4, which is 17 4. As I've always suggested, improper fractions are easiest and neatest to work with. And so, we've got a stationary point at negative half, 17 4. Now we need to determine the nature. And as we said, in order to do that, we've got to test. We test our x and our f dash x. So we want to see what is the gradient doing on either side of that stationary point. So we know with our first one, which is our stationary point minus a half, is always, as we said, going to be 0. Then we want to test just less than negative a half. Let's go with negative 1, because that's close enough without being a difficult number to use. When we sub negative 1 into our f dash x, we get minus 1 minus 2 into negative 1, which is minus 1 plus 2, which is 1, which is a positive number. Remember, it doesn't matter what the number is, we just want to know what is the gradient doing. Is it increasing or is it decreasing? So we know it's a positive number. Let's try a little above negative a half. A good number to use there is 0. Sub in 0 into our f dash x, we get negative 1, which is a negative. And so if you sketch out manually what our gradient's doing, it's increasing, then it's flat, then it's decreasing. Which means, as you can clearly see, we have a max. And so that part there was just our testing of the nature. And we proved that we have a max at minus a half 17 on 4. So hopefully that went well. Let's scale it up a little now. Find and determine the nature of any stationary point or points of the curve f of x equals a third x cubed minus 2x squared plus 3x minus 9. Alright, definite intimidator. A lot more terms, a lot more to work with there. But let's give it a go. There's our function. We know the first step we're going to have to do every time, differentiate it. So bring the 3 down and times it by the third and cancels. So that becomes x squared minus 4x plus 3, and the minus 9 disappears. So it's starting to look a little neater for the f dash x. We can leave it there for now, or if your instinct tells you straight away, which mine kind of does, I always look, when I see a quadratic like that, I always think to myself, can we PSF it? Can we factorize it? Because if you can, it's often easier to work with. In this case, you actually can. If you use your PSF, you get x minus 1, x minus 3. So from there, or whether you did this now or in the later step, you know that stationary points when the derivative is 0. So 0 equals x minus 1 into x minus 3. So whether you factorized it before or now, you'd get to the same point. Which means we know from quadratics that x will then be 1 or 3. So this is interesting. We've now got 2 stationary points. We've got one when x is 1 and one when x is 3. So this is why this is a little bit harder. Let's test with each of those. Sub them back into f dash x. So when x is 1, I've done all the work in there for you. So you just replace 1 wherever there was an x. So you'll end up getting a third minus 2 plus 3 minus 9. Again, probably calculator's best. So you get minus 7 and 2/3, or improper fraction, minus 23 and 3. Ugly numbers, I know, but it doesn't matter. We will get the marks for it, and all they're trying to do is throw you off the scent with these ugly numbers. Often people make mistakes with these harder numbers, or they think they're getting it wrong. But just persevere, just go nice and carefully, don't skip any steps, and you won't make any mistakes. Okay, let's sub in our f of 3. Same deal, we just replace, wherever there was an x, we replace it with a 3. And you can see all the work I've done there, probably calculator it, and you'll end up getting minus 9. So our 2 stationary points are 1, negative 23 and 3, and 3, negative 9. Those are 2 stationary points. What we now need to do is we need to test them. So we'll draw out an extended table this time. You can do them as individual tests, or you can do it all in one table, which I found a little easier. You can just save a slight step. We know we want to test at x is 1 because we know there's a stationary point there. And we want to test at 3 because there's a stationary point there. And now we want to test on either side what is going on. So let's start off with a little less than 1. We'll test x is 0. So we sub in 0 into f dash x. When we do that, we'll end up getting, as you can see there, 0 minus 0 plus 3 is 3. So we get a positive gradient. Now we'll test our 2. That 2 falls between the 2 numbers, so we kind of kill 2 birds with 1 stone in a sense. So that 2 will then test into our f dash x, and we land up getting negative 1, which is a negative gradient. Then we test our 4, sub that in, we land up getting 3, which is a positive gradient. So when we do our little manual sketch like we were talking about before, we've got a positive gradient, flat, negative gradient. And so we know at that point 1, negative 23 and 3, we have a max. Then we've got flat at 3 and positive at 4. And so at that point 3, negative 9, we've got a min. So we can just do a conclusion or summarizing statement and say, therefore, a max at 1, negative 23 on 3, and a min at 3, negative 9. That is a lot of working, I know, but you can see how it's kind of systematic. It's step by step. There's nothing really new, but there's just a lot of working. So you've just got to persevere and just be patient throughout it. It is a harder question. They're not going to get all that much harder than this at this stage. So if you're following that, we're on top of it. So let's summarize the first derivative. There's two main functions of it. First one is that it describes the gradient or slope of the curve. So we can see exactly what the gradient or slope of the curve is doing anywhere by just looking at the first derivative at that point. For example, if the first derivative is greater than 0, it's a positive gradient, so it's sloping up. If the first derivative is less than 0, it's a negative gradient, so it's sloping down. And if the first derivative is equal to 0, well, that's what the major second point is. The first derivative helps us to find stationary points, something that will become an enormously crucial process over the next year or so. The way we do it, as I said, is when y dash equals 0. So you let y dash equal 0 and you will solve and find your stationary points. However, you also need to determine the nature of the stationary point. And we went through a manual method to test either side in terms of its y dash, so you manually draw it out and see exactly what happens. But the good news is we're about to learn a much better method for determining the nature, which is pretty exciting.